Hello and welcome everyone to today's webinar on why Kubernetes is an important choice on your digital transformation journey. My name is Lorenzo Galelli. I'm a solution architect here at IONOS Cloud, and I'm joined today by one of our strategic partners, Red Maple. With me is David Griffiths, who's the CIO and Chief Engineer at Red Maple, who will be taking you through this topic this morning. So with that, I'll pass over to David to introduce himself and start the session.
Okay, thank you, Lorenzo. Welcome everybody. My name is David Griffiths. I'm a director and the CIO at Red Maple Technologies. I've been a software engineer all my working life, which is about 25 years now. At Red Maple, I develop containerized solutions, cloud solutions, and help companies transform their businesses securely and their services for the online digital age. So today I'll just go through what I'm going to cover in this session. I'm going to start by talking about digital transformation itself, what it is, and why it's important for businesses. I'll also talk a little bit about the types of challenges that we see at Red Maple. So a particularly good route to consider when looking at digital transformation and modern web services in general is containerization and the orchestration of those containers in a microservices architecture within cloud deployments. So I want to go through a quick journey, starting with containers and what they are and their benefits, through the concept of Devops and cloud native applications, and lead on to Kubernetes. I'll give an overview of what Kubernetes is about, and then I'll hand over back to Lorenzo, who will run through a practical demonstration of the managed Kubernetes services provided by IONOS. So digital transformation. What exactly do we mean by digital transformation, and why is it important? And also, why is it hard? Digital transformation doesn't really have a precise definition, but to me, it's a reimagining of how an organization uses technology to fundamentally change their business's performance, their customers' experience, and their efficiency and effectiveness. It's a way of using modern digital technologies to solve problems that are new and in more effective ways. But it's much more about technology. It's also about cultural changes and operational changes within an organization. And this is one of the reasons why it can be so tricky to perform successfully. There's a lot of evidence to suggest that businesses are not very successful at digital transformation, with about a 70% failure rate. But why is it so important for businesses to do? So my view on this is that the world is technologically a very different place to what it was 5 to 10 years ago. Cloud and web technologies have changed what services are possible to provide without large initial investment, and the fidelity of what can be achieved through modern technology, open source and good design is much higher. So in many ways, cloud is a great leveler, since it allows small businesses and startups to take on the incumbents and provide better services. Also, everyone now carries a mobile device, and every desktop and laptop has a browser installed on it. So it's much easier and simpler than ever for an online service to reach customers anywhere in the world. And all this means that for established businesses to compete in the modern world, they need to be able to make the most of the technology that's available, or risk falling behind those that do and will use these things better. So one example, a continuous delivery where services are constantly updated and improved. It's now an expectation online that that's the case. However, as much as digital transformation is not just about technology, today I do want to just focus on the technology side. Oops, sorry, gone the wrong way there. Okay, so what are the sort of that we see at Red Maple? Well, we're primarily a professional services company specializing in cybersecurity. We often begin our engagements with clients through a cybersecurity assessment or an incident response. But generally, as we better discover what our clients' needs are and how we can help them best, we often find at the heart of it is a digital transformation problem, whether that be the migration of a service or system to cloud, and doing so securely, or the development or uplift of an existing product. Hence why digital transformation is a growing part of our business. So we see what things we tend to see. Well, we see existing legacy applications that companies have that are monolithic. They're not containerized and struggling to scale. Where you see systems and processes that are very manual, for example, spreadsheets and access database systems. We've all seen those, and need of transforming and updating the workflows, which need better data management and better automation. We see applications that are most of the way through development, and then someone thinks about security, and also new software as a service applications. They're going to be built from the ground up, maybe to replace an existing system. But whatever the challenge, the important thing is to get the system into a state where it's secure, it's reliable, manageable, and also scalable. The principles to achieve this are really nothing new. You need a system architecture that's kept simple, made up of encapsulated components that are easy to maintain, that use modern up-to-date technologies and are easily replaced when the need arises, and which can be scaled to meet increased demand, preferably dynamically. And containerization is a great facilitator of this, is why I want to go on to that next. So what are containers? Containers help companies modernize by making it easy to scale and deploy applications. And they're a way of running software in self-contained environments that are abstracted from the underlying host OS and the hardware. They are an entire runtime environment, an application plus all its dependencies, libraries, other binaries, configuration files needed to run it, all bundled up into one package stored as an image. In this sense, they are a bit like virtual machines, but they are much lighter weight and start up almost instantly. They don't contain a whole operating system like VMs. Each container shares the host operating system kernel with other containers. And they're truly portable and can run virtually on any OS with a container runtime environment installed. The most familiar of these, of course, is Docker. A container image may just be a few tens of megabytes in size compared to a VM that is typically many gigabytes. That said, though, if you install a lot in your container, it can get quite large. You generally only run one main process in a container, and that provides just one service. And particularly in a production build, you only install the things in the container that the service requires to run, so you keep it down in size, and you also reduce the attack surface area. Docker containers are specified using Docker files, which determine what is installed in the container. They're built using layers that are additive and cached, so changing the top layers doesn't require rebuilding the lower layers. The base layer that you build from will, in practice, be either a public OS environment, such as Ubuntu, Fedora, Alpine, etc., or it'll be an OS plus a service. So, for example, you might start from an image of Nginx in Alpine and copy in some HTML and JavaScript files of your own, described in the Docker file, and hey presto, you've got a web service. Building container images is usually very quick, since you're generally only building the last few layers. So, taking a broader look at the benefits of containers, and they're very versatile. Anything you can run on a general server that doesn't use special hardware is, in theory, reproducible in a container. They are very portable, since they abstract from the underlying OS, and this helps greatly with the ease of development and testing, because you can run the same environment locally. Deployment is more versatile, since you just replace the container that you need to. When it comes to container orchestration, like Kubernetes, this live replacement, or rolling update, as known, is very important for maintaining a live system, since there's no need to tear it all down. Scalability is a huge factor in all of this, and containers make it much easier to scale your service by replicating containers. They're very easy to run. A single command, literally a single command, can have a Postgres server, for example, running in seconds. There's nothing to install. Very easy to maintain and update. Very efficient and lightweight, and a fast startup. I mean, the resource efficiency, you're able to configure disk space, memory usage, libraries, and binaries to load in your container that you need. So you can kind of create the lightest weight container that you need, which just has the environment that it needs and nothing else. They have a native performance of the host OS, And they're really perfect for designing a system of decoupled components that communicate, for example, using a distributed messaging system. I mean, there's often no need to actually even build the container yourself, because often you can use images built by experts in the field in particular that allow tech providers to provide a very well configured container. So, for example, if you want to run a Postgres container or a Mongo, you just go for the one that's provided by those suppliers. They're very easy to keep updated. I mean, how many times do you see a legacy system using, for example, an old version of a database server that's never been updated because it's deemed to be too risky or too much effort? And actually, this is an important principle that I want to get to with DevOps, is the concept of reducing the barrier to updating components of your system, and having a concept of being always up to date. More on that later. There are security benefits of containers, definitely. I mean, they offer an improved process level isolation. Their attack service for an individual container is generally a lot lower, since you only have to have what's needed to be installed in it. Although I do want to caveat all that, of course, with saying that a poorly configured system will still be insecure, so it's not a silver bullet, I think. And all this really lends itself to a more continuous and agile way of developing and operating services and applications, known as DevOps. So I want to talk a little bit about that. So DevOps is really an extension of an already established agile software methods. It combines the practices of development teams and operator teams. Prior to DevOps, in simplistic terms, there were development teams and operator teams. The developers wanted to create lots of features and make the coolest applications they can, whilst the operators want things to work, to be stable, to be available. And they don't like lots of change, because with change, things can break. And this approach creates a lot of conflict of interest between developers and operators. And the interface between the two tends to be a wall, which every now and again code is flung over by the developer. There are usually agreements between the two as to how often code can be flung over the wall, and this is generally defined in terms of release cycles. So a product or service might have a release cycle maybe of every 3 months, and features might be developed according to that release schedule, which kind of works, but software and technology doesn't always fit into predefined fixed size boxes, like every 3 months. So a feature might be rushed in order to meet the next release, or it could be finished but not actually provided to the customer because there's no release coming up for the next month. And this results in at least 3 bad things. There's a lack of agility, a lack of quality, and also, I would say, a lack of ambition, because the temptation is always to play safe, so things don't break, and to put up with issues in the software that ultimately annoy customers. And DevOps takes a different approach to these two roles. It's a completely different mindset, really. Software is developed and deployed all the time, continuously. There's no more release cycles. Everything is continuous. As much as possible is automated, and as much as possible is measured, so the state of everything is always known. If things go wrong, you can simply roll back. The developers are encouraged to be bold, to think big, to just try stuff out, and not to be afraid to break things. And this achieves agility and lets great ideas flourish and reach customers quickly. The upstream dependent libraries are regularly updated, meaning security holes are quickly patched. The system never goes stale and out of date, and new features of third-party and open source libraries can be used straight away. So, one might ask, well, how on earth is stability and reliability achieved in this model, since it seems a bit counterintuitive, you're updating things all the time? But in reality, this can be managed in other more efficient ways, like having a concept of staging features into release channels, such as alpha, beta, stable. Problems are detected before they reach the production stable release, yet there's a steady flow of features and updates reaching production all the time. However, all this does require good tooling and good automation in the areas of build, integration, and deployment. And this is where containers and Kubernetes can be of great help. But before I get onto that, I just want to mention quickly about microservices and cloud-native applications. So microservices follows the traditional principle of software engineering, really, that many types of applications become easier to build and maintain and test when they're broken down into smaller composable pieces which work together. However, the true benefit of microservices comes when one considers scalability, isolation and resilience, deployment, and the ability for many of the components to be off-the-shelf open source tools. So what are microservices? Well, microservices is an approach to software architecture that builds a large complex application from multiple small components that each perform a single function. Each microservice is a distinct unit within a software development project, and has its own code base, its own infrastructure, and perhaps a database as well. They work together, communicating through web APIs or messaging queues, respond to incoming events. So the aim really is to move away from the monolithic services, like on the left there, that only scale vertically, really by just running on a more powerful machine with more RAM and CPU. But I mean, why not monoliths? Well, I mean, successful applications have a habit of growing over time and eventually becoming huge and too complex to change and maintain. And from then on, really, all attempts to be agile will flounder. And there are other reasons why monolithic applications can run into problems. They can be quite inefficient since an application always consists of different types of things with different resource needs. Yet in a monolith, they generally end up all running on the same hardware, which is always a compromise. Okay, so Microservices Approach takes a more separated approach to this. All the services can be written in different programming languages potentially if you need to be. You can build an application as a suite of small services, each running its own process and independently deployable. So in order to actually achieve an application based on microservices, you need to be able to monitor, manage, and scale the different constituent parts. And this is where an orchestration tool like Kubernetes comes in. So let's look at Kubernetes. What is Kubernetes? Well, Kubernetes is a container orchestration platform. It's designed to automate the deployment, scaling, and management of containerized applications. It's designed on the principles of scalability, availability, security, and portability, and optimizes the cost of infrastructure by distributing the workload across available resources. It's very much now the de facto container orchestration system for the cloud, and it's provided as a managed service by all major cloud providers, including IONOS. Kubernetes makes it very easy to deploy and operate applications in a microservices architecture by creating an abstraction layer on top of a group of host machines. In Kubernetes terminology, these are called nodes. These nodes, together with a master controller in the center there, form a cluster. So a node is the fundamental resource for CPU and memory. They can expose compute, networking, and storage resources to applications. They might be virtual machines in a cloud or perhaps bare metal servers in a data center. You can set up a cluster with as many nodes as you like and even get them to scale automatically. So there's more on that later. You configure nodes into what's called node pools, which are pools of nodes of the same type. So in the diagram there, you can see the basic architecture of the Kubernetes cluster. Shown there are 3 nodes, host machines, in the cluster, controlled by a master shown in the center. The master exposes an API for deploying and managing the cluster, accessible by various authenticated methods. But the one you'll most likely use is kubectl. At the bottom there is one of a topic of much pronunciation debate, how to pronounce it, but I'll call it kubectl. It is the CLI tool essentially for interfacing with Kubernetes. Now, running on the nodes are various containers. These run in logical units known as pods. More on that in a sec. But the important thing to note is that the master controller will have been instructed via a configuration file to run these containers, but not told precisely where. You can give all sorts of hints in the configuration, but in general, it is up to the master to determine where best to put them. And this provides a good abstraction layer from the underlying machines. For example, the green containers you can see there might be a Mongo database with a master and 2 slaves. And Kubernetes has done the sensible thing, and it's spread them across the 3 nodes, maximizing the resilience should one of the nodes go down. Now, if a node does go down, then the master will automatically reschedule containers that are running on that node onto the remaining nodes if it can. Resource constraints permitting, obviously. Alternatively, the process running in a container might crash or lock up, in which case Kubernetes will detect this and automatically restart that container. I mean, should this happen repeatedly, it will eventually give up and the container will be put into a state called a crash loop back off. But in general, in a production system, you wouldn't expect your containers to be crashing all the time. So that's more what would happen in a development environment. In the configuration of the master, it will have been told which container images to run. So at the top there, you can see the container registry. So the master will go and fetch these containers from the container registry where they are held. And this might be a public registry like Docker Hub, or it could be a private registry. So at this point, what would be useful is to look at the Kubernetes resource hierarchy to understand some of the basic building blocks. Okay, so the first most fundamental component is pods. These are the basic execution unit in Kubernetes. They're simple objects, the simplest object you can create or deploy in a cluster. A pod encapsulates a container or sometimes multiple containers. And it is like a wrapper that provides containers with resources and a unique IP on the cluster's internal network. Pods act as the logical boundary for containers, sharing the same context and resources. So the time when a pod might consist of more than one container is when multiple co-located containers are tightly coupled and need to share resources. Every container in a pod shares the same network space, including the IP address and network ports. So containers inside a pod can communicate with one another just using local hosts. Pods can define storage volumes that are mounted into the root file system of the container. All containers in the pod can access the shared volumes, allowing those containers to share data. Now, although you can, you typically don't deploy pods directly to a Kubernetes cluster. They are generally designed as relatively ephemeral and disposable. So instead, what you do is you create a controller that manages and looks after the pods. And the most common example of such a controller is called a deployment. So a deployment is defined via the API. You send a configuration file. You can see an example on the left there. And the deployment logically resides on the master and describes a desired state. So for example, in the configuration you can see there, what we're saying is, can we have three instances, three replicas of an Nginx container, and the image definition is down the bottom there, Nginx 1.14.2. So that's all the master needs to go off and fetch that from a public registry. It exposes port 80, and that's it really. And you send that to the master, and it will create those three pods for you. That's container replication, and it's running multiple instances of the same container. And a typical pattern is to have at least three instances, each running on different nodes to provide an uninterrupted service. Kubernetes manages this deployment automatically, which is very good for reliability, load balancing, and scalability. However, each pod in the replica set has its own unique IP address on the cluster network. And in a deployment, the set of pods running at one moment in time could be different from the set of pods running that application a moment later, because pods can come and go if they crash or the node goes down, etc. Things can come up. So this raises a couple of questions then. And how do the consumers of those pods discover those IP addresses, and how do they spread the load across all the pods in the replica set? Well, the answer to that is services. Now, a Kubernetes service is a permanent abstraction which defines a logical set of pods and a policy by which to access them. In a microservices architecture, this defines a microservice ultimately. A service gives a set of pods a DNS name, so consumers can add the service via a DNS entry rather than having to remember IP addresses. Also, a service will automatically load balance traffic across the pods in the service. In the configuration, you define which pods a service fronts via the selector definition. So you can see here on the left definition of the service, it has selector of app Nginx, and that correlates to something in the deployment selector, which will tie those three together. And there are a few different types of service which define different ways of exposing the service to consumers. A couple of very common ones. Then the default one is called a cluster IP, and this type of service exposes the service on an internal IP in the cluster, so it can only be reached from within the cluster. Another type is a load balancer, and this is a standard way to expose a service on the internet. An external load balancer is created and assigned a fixed external IP address. So there you can see you can just by setting the type, you can define whether or not you want the service to be only available locally within the service or externally. Just talking about a couple of other features of Kubernetes while we're here, just to finish up with, and I'll pass over to Lorenzo. One of the features is rolling updates and rollback. Now, zero downtime deployment can be achieved by rolling updates. What happens is before Kubernetes shuts down existing application containers, it will start spinning up new ones and incrementally update pods with the new instances. Only when a new one is up and running and correctly running does it get rid of the old stable release, and it does this incrementally. But it's important to say that Kubernetes has a built-in rollback mechanism. So if the worst does happen and the new pods, where they come up and run, they're doing the wrong thing, you can quickly roll things back. Very simple through a command. The other example I wanted to finally mention was automatic scaling according to workload. Now, this is obviously one of the things that you want to be able to achieve with scalability, that your system can scale on demand. Now, there's two ways of doing this. One is through the horizontal pod autoscaler. This has a control loop which defaults to every 15 seconds, and during each period, the control queries the resource utilization against the metrics specified in the horizontal pod autoscaler definition. And the controller obtains the metrics from either resource metrics API, or even you can provide custom metrics API if you want to scale according to something else other than, say, CPU. And the autoscaler compares the actual metrics with the defined resource request of the pods, and it scales it accordingly, creating or destroying pods as necessary. The second way of auto-scaling is cluster auto-scaling. This is something that is supported by all the major Kubernetes providers, including IONOS, and this is where you automatically adjust the size of the cluster to the workload. So essentially you are adding more nodes or moving nodes as necessary. If the resources necessary to run, say, a new pod are insufficient, the autoscaler will automatically add a new node to the existing cluster. So that's a bit of a whirlwind tour of Kubernetes, and hopefully from all that you can understand that it's a great way of providing services in the modern age and performing digital transformation of existing services. So I'll hand back to Lorenzo now for a quick demonstration on the IONOS platform. Okay, Lorenzo?
Yeah, thank you, David. That was really informative. Yeah, it was really good. Thank you very much. Okay, let me just share my screen. So hopefully you can see my screen at the moment. David, if you can confirm that you can see it as well. Just
yes.
Okay, perfect. Okay, cool. So what I'm going to do is just go through how quickly, I guess, you can create a Kubernetes cluster, and I'll give you an example really of that Nginx deployment of what that looks like as well. So within the IONOS dashboard, you have a section under Manage Resources called Kubernetes Manager. And what this allows us to do is basically create the cluster, the control plane with the masters, and also the worker nodes inside the node pools for the placement of the pods, containers, resources, etc., which we'll be running. So really to get up and running, it's a matter of initially creating a cluster. So what you do is obviously give it a name. So this is going to be for my QA team. And then we can also choose a relevant version. So Kubernetes brings out, I guess, new releases or updates every quarter. And we also update our availability in relation to those versions as well. And you notice we're pretty much up to date on the relevant versions available to you for deployment. What I'll do is I'll just stick to 16.6 at the moment and then click on Create Cluster. And what's happening now on the back end is that the master control plane is being deployed and provisioned across the multiple data centers in the IONOS cloud. Another huge benefit, I guess, of using our managed service is that the control plane is actually free, so you don't pay for the control plane, which is quite unique. Even Google, Amazon, and also Microsoft are now charging for the control plane clusters themselves. So again, another benefit, I guess, of using our technology. This takes about 5 minutes or so to get up and running. Once it's there, then it's a matter of looking at the relevant cluster. At that point, you can download the kube config, so you can use kubectl or kubectl, whatever we want to pronounce it, to get up and running. What you will do, though, is you need to create a node pool, which will be your worker nodes, which will host the relevant pods and service. So it's a matter of clicking on Create Node Pool, give the node pool a name. So this is for my DevOps team, and they're working on the app. And then I can also select, either create a new data center directly for them, so a virtual data center, or I can choose one which I've already created in this example. I can then specify how many worker nodes I want in the cluster. So this is going to be a standard 3-node cluster for the worker nodes. And then I can select the architecture that I want to deploy for those. So here I'm just going to choose the Skylake processor. Number of cores are okay because it's really just for the DevOps team. I can also increase the amount of RAM that each of those nodes in the cluster is going to consume as well. So again, another huge benefit really is that there's some flexibility in the sizing that you can apply as well. So you're not stuck in a certain size in relation to the deployment. We also have the concept of availability zones as well. So these are resiliency zones which you can then deploy the worker nodes across. I'll leave it as auto for the moment and it'll work it out itself where things should go. And then the local storage, which is going to be the root file system for the worker nodes, I can then either use HDD or SSD depending on what I'm going to be creating for the cluster. I'll just use HDD as it's just the DevOps team. They don't need anything hugely powerful. And then click on Create Node Pool, get validation, and then off I go. So what's happening now on the back end is the node pools being created for the DevOps team. That'll probably take about 10 minutes, which we're obviously not going to sit and watch through, but I now give you an idea of really how to get into the cluster and start deploying stuff. So I've already got a cluster created in true Blue Peter style. I've got the QA test, which is a 2-node cluster running a certain version, and you can see there the configuration in relation to that cluster as well. And then it's a matter of really connecting in using kubectl to work with the environment. I mean, that said, you can also deploy the standard Kubernetes dashboards as well as standard I guess applications for monitoring, deployment of environments as well. So things like Istio, Helm, Prometheus, Grafana, all the relevant tool sets that you may be using can also work on our platform. So you're getting an upstream version of Kubernetes, and then you can obviously start deploying the environment itself. What I've done, I've connected already. I'm using kubectl. I'm looking at the nodes. So there's a shorthand acronym for nodes there, and I'm getting a status which will give me more information. So you can see the version that's running. You can see the base operating system image that the worker nodes are built upon, and also the kernel and also Docker versions which are running as well. And then what I'm going to do is I'm going to deploy that Nginx deployment YAML file. So if I just show you that now. So that's the YAML file we're going to deploy. We're doing 2 replicas because I've got 2 nodes which are running, so I'm going to split across the 2. And I'm using Nginx as that deployment as well. Okay, so let me get up and running. So I'm just going to go into Tmux a minute, and then I'm going to split the screen. And then what we're going to do is going to watch the output, just so you can see what's happening in the environment as well. So kubectl. I'm going to get the pods which are being created. I also want to look at the services which are being created, and I'm also going to look at the events as well, which are already running, I guess. So we'll let that go. We'll see that it's going to start creating information into the IONOS namespace. So Kubernetes can use new namespaces for logical containers of resources, which is a good best practice to utilize. So here I'm just going to use that for that purpose. So the first thing I'm going to do is going to basically deploy the Nginx deployment itself. So for that, I'm just going to write in kubectl. I'm going to apply a file, which is going to be the Nginx deployment YAML file. So as I execute that, what we'll start seeing is the containers being created. We'll see some events underneath in relation to pulling the image. As David mentioned, it's pulling from the GitHub source at the moment in relation to, Docker Hub in relation to Nginx. So that's pulling, everything's there. So we can see, systems are running, the containers are in a running state at the moment. And at the moment, port 80 is open, but it's internal. And ideally, what I want to do is expose the Nginx application to the outside world, so I can connect to it and just make sure things are working. I could use the YAML file to do that, but I can also run a kubectl expose command, so I can expose elements of this deployment to a service. So I'm just going to run the deployment. Nginx deployment. I'm going to add the type of load balancer. I'm also going to give it a name, again, just like tagging or labeling the relevant service which is running. So this is going to be my web service. Yep. And then what we should see is a service being created for that and exposed as well. So I'll just run that. Oops, did I type something wrong? Oh, type equals even. There we go. Okay, so now we can see the load balancer service being activated. What we'll eventually see is an external IP address. So this will be visible to the outside world. So once it goes there, I mean, if you want to, you can use the IP address and obviously see if it's working. So I'll just copy that at the moment and then go back into my browser, paste that. And there we go. We've got Nginx up and running. That's all cool. And the application is now available. So the other thing we can do is do scaling, obviously, as well. So what I can do is I can use the kubectl command to scale. So this is going to be a manual scaling of the replicas which are running. Oops, replicas equals 4. I'm going to run that against the deployment of Nginx deploy. And then what we should see is additional 2 containers being deployed across the relevant physical nodes, I guess, of the worker node as well. So I'm just checking my typing, make sure it's correct. There we go. And there we can see 2 more containers now running. And we have those environments up and running, etc. as well. So as you're testing my app, I can obviously scale that accordingly. I could use the horizontal port auto scaling for that capability, or I can, obviously look at the physical nodes as well, and then utilize an auto scaling via API for that also. So that was it, really. I just want to quickly show, how we can deploy something in a cluster, how easy it is. Yeah, so hopefully it gives you some insight, really, how to create things and how easy the implementation of that process is. I'll just go back to my environments. So we can see the QA team is now up and running, so I could obviously create no pools for that. If I look at the Devops team, that's currently still in the deployment state at the moment, but eventually we should see access to the cluster. The last thing I just want to make a note of is the kube config itself. So typically to connect in, what we do, if I just exit out of tmux a minute, and there we go, exit that. So what I've done, I've basically exposed or exported the kube configuration. So if I look at /root/kube, and then what we'll see in here is the kube config YAML file, and it's then a matter of sourcing that in relation to the actual file itself. Once it's sourced, we then can actually connect in. There were some other webinars which I did create previously, which gives in a bit more detail about using our platform, using things like persistent storage, volume claims as well. So those are quite good webinars for further information if you want that. Okay, I'll just stop sharing my screen at the moment. I'm just going to cut to any questions which may be there. And if you have got a question, there is a chat window which you can connect to and fire your questions there. So I've probably got one question actually for David. In relation to, I guess, the customers that you have spoken to, what is the key challenge that they typically have? You know, because obviously going the Kubernetes route is one thing, but you know, what is the key challenge that they would need to overcome, I guess, to go down this route?
In order to move on to a containerized system, you mean, or Kubernetes? Yeah. I mean, generally a lot of it is just the kind of the know-how, I suppose, or just not knowing where to start. I mean, they quite often will have a legacy application that may be a monolith or something like that, and even if it isn't a monolithic application, it's kind of all kind of tied up with itself. So one of the things that we do, I mean, obviously one of the first things we generally will be looking at is the security of the system. When we move on to the digital transformation side of it, where you'll tend to see what components of the system can be extracted and separated from one another, and put into a containerized environment. And as soon as you start breaking things up a bit, they become much more manageable. And the sort of problems that we see are, I mean, this is one of the things why it's so hard to do in many ways, digital transformation, is because you've got a system potentially that's been running for a long time, and it does what it needs to do, and suddenly you've got to sort of migrate it into the cloud environment or into containers or whatever. And the path by which you do that is often the biggest challenge. That you can obviously just do a complete rewrite, but that's not obviously on the whole not a fantastic solution. But often there are ways to do a gradual move, and it's the stepping stones from going where they are to where they need to be, which is often where the real skill comes in, and the kind of the know-how of how to do it. So that's, I say, technically is probably the thing that we tend to see. Yeah.
Okay. Yeah, it's similar to the conversations I guess I'm having with customers as well, is to understand, I guess, their application and how they break it down into smaller chunks. One question that's come in is regarding the resilience of the master nodes themselves. So yeah, when we deploy that cluster, those master nodes, so there's typically 3 master nodes which are created for our control plane. Those are spread across different data centers, and that provides a level of resiliency if obviously one data center goes down, which is something which hasn't happened, I guess, in the IONOS history. Then the other nodes are there to take up the slack in relation to scheduling, configuration, etc. as well. So yeah, resiliency is taken care of regarding that. Okay. The other thing I was going to mention is obviously you can build, the cluster yourself. I've got a script which sort of goes through that. I think one of the key challenges is, to create the cluster it can be quite straightforward to do that. It's the updating, the patching, keeping up to date on the relevant revisions. That's really the hard bit. And when you look at a managed service to abstract that away from your operational cycles, then that's really where the key benefit comes in. You don't have to worry about the infrastructure. All you need to worry about is the application that you're providing to the business, for your customers, etc. as well. So that's one thing I just wanted to bring out.
Yeah, I think that's definitely
Okay,
true.
so
Especially I think when when the master controller plane is free as well, then it like it is with IONOS. I think it's there's very little point in sort of instantiating Kubernetes yourself really. It's very
yeah,
much managed services is really quite a clear choice.
yeah, absolutely. Thank you. Yes, okay. Right, we're up to quarter two, which I think is on our time. I haven't got any other questions at the moment. This session is being recorded, so you can log back in again with your credentials and you can view it at your leisure if there's elements there which you are not fully 100% on. You can also obviously contact us and we can help you with any questions you've got. And also, if you want to try out the Kubernetes platform, that's something that we can also assist with and help you going forward as well, along with obviously working with strategic partners such as Red Maple. If you've got any application type development and transformation that you want to provide.
Absolutely. If anyone has any questions for me, yeah, just I'm David at redmaple.tech. Just look me up. No problem.
Cool, thank you, David. And again, thank you again for your time today as well. That was a really informative session on Kubernetes, which is really good. Thank you. Okay, so with that, thanks again for your time today, and thank you for joining the webinar.